The
Okay.
stigmergy, the emergent coordination through the environment. So let's quickly go through the table of contents. First, we are going to start with the definition of the stigmergy and its short history. Then we are going to discuss the 4 basic types of this stigmergy. Then we are going to quickly show applications of stigmergy in describing the dynamics of the human's behavior. And we are going to finish the presentation proper by going through the one of less famous but very interesting experiments in using stigmergy in robots. So let's start. What is stigmergy? The word stigmergy comes from 2 roots. Stigma, meaning sign or mark, and ergo, work. So, this stigmergy means the coordination of work through the environmental markers. The original term was coined by the Pierre-Paul Grasse, the entomologist working on modeling the behavior of the eusocial insects, in his case, the termites. The model of stigmergy, that's it, that the individual agents communicate through changing their environment, was created as the alternative to the 2 prevailing theories. In the late 50s, there were 2 conceptions of the high-level organization of the simple agents. The theory of the superorganism, where the whole colony was treated essentially as the organism with the individual agents as its cells, and the theory that the agents aren't really communicating. They're simply doing their individual jobs just close to each other. This Grasse suggested that the agents aren't creating any superorganism. That's it. There is no central imperative dictating their actions, but instead they are communicating with each other through changes in environment. Now, let's look at the example from his work. The mechanism of construction of the pillars in the termite nests. Here we have the simple algorithmic schema of the construction. The individuals are creating the mud pellets, which are marked with their pheromones. They are gathering pellets in the pile. The pheromones, our markers, are giving signal to gather more pellets in the same place, which in turn creates the incentive to bring back more pellets, as the bigger pile has the stronger pheromonal signal. Once the pile reaches the critical mass, the pheromone concentration signals creation of the pillar. As we can see, this step-by-step process isn't tied to any specific worker. Any worker who understands these chemical signals can follow. Now, you may ask yourself how the system stops itself from creation of multiple piles below the critical mass. Here, We can see the explanation of how it's solved by seeing the three-dimensional graph showing the formations of pillars. In this case, the termites were essentially placed in such a way that they got only 1 degree of freedom in movement. So the pillars were formed essentially as one-dimensional stacks behind the glass. I think that the glass was used because, yes. So now the y-axis is the location. The x-axis is the time. Time progresses in this direction. Yes, this. And the z axis is the size of the individual pillars. As we can see at the beginning, we have essentially wavy sand that can be treated as roughly uniform distribution. That's it. Well, not truly flat surface, but rather this distribution in a uniform pattern. Now, the termites are working essentially random. Yes, yes. They are creating pairs and bringing them into piles. But at the certain point, roughly about here, one or two of these piles become big enough to trigger creation of the pillars. It happens because the stigmergy amplifies these small perturbations in the environment. The feedback loop shown here, yes, the feedback loop shown here means that over time, even if one pillar starts getting built, it will trigger the reaction that changes how pillars are built elsewhere. So, now let's discuss the basic architecture of Stigmergy. We have seen how it works in terms of the termites. Now, there are two most important factors in Stigmergy: the agents and the environment. Agent is, in this case, the limited self-contained unit that perceives the environment through sensors and acts upon it using actuators. The internal state of the agent is hidden from the other agents. That's it. The termites don't know what other termites are doing in particular. They only know what they can perceive right now. The environment is, in this case, defined as space, not only as space, but as a certain system, spatial system in time. Yes, the certain topological system changing over time. So, as we can see, this the internal state of agents dictates its actions, right? The dynamics of agents, or in other words, its instincts, behaviors, or programs, depending on how we define agents in particular, are influenced by the two feedback loops. The feedback of its internal state, in which case this part is simple finite state machine, and its environmentals. Its environment, in this case, the state of the environment, which also is changed by its dynamics and interactions with the agents. So, what defines the agent? It has internal state, which isn't directly visible to the other agents. It has sensors to observe the world around it. It has actuators to modify the environment. And it possesses the internal dynamics based on its internal state and the sensor's readings. In other words, it reacts to the environment and its own internal logic. The environment, on the other hand, possesses the topology, that's it, it has certain structure, its internal state, which is, in this case, essentially everything going around in the environment at a given moment, and its dynamics that govern the evolution of its state over time. Now, how these agents communicate. We have talked about the pheromones and the markers. Now, these methods of the Stigmergy communication have the four basic categories depending on the method of communication. First, let's discuss the marker-based methods. The marker-based methods are all methods where the agents create certain specific markers that aren't simply basic rearrangements of the environment. For example, all pheromones, tags, or even graffiti can count as the marker-based communication. Now, the marker-based communication can be differentiated between quantitative and qualitative. The quantitative communication, there is essentially one type of marker existing at the different concentrations, just as the pheromones were, yes. And in case of qualitative, there are multiple markers. The sematectonic communication is one where the only changes are the changes in environment. Essentially, the changes in topology and the structure and the objects in environment are signals themselves. Examples include these ants building the cemeteries based on the concentration of dead ants in area, and wasps selecting the new placement of the new cells in nests based upon their based upon the other cells around a given point in space. Now, let's begin our discussion about the human Stigmergy, starting with the simple example of the trail formation. Yes, I'm pretty sure that everybody is familiar with the fact that humans will trod the paths that are more, shall we say, convenient by themselves. Now, let's analyze this from the point of view of Stigmergy. Our environment is the vegetated terrain. Our topology is to the manifold, roughly. It's the state of the environment is the degree of ground covered obstacles, and the dynamics are basic. The trodden vegetation dies, and untrodden paths get covered with grass again. The agents are people. Their sensors are the sematectonic. Essentially, people follow these smooth paths in the direction to their destination. And marker-based. We can read the road signs designating the paths. Our actuators are sematectonics, the direction of our next step. Essentially, we can throw the grass. And marker-based, we can path the paths and set up the road signs. The dynamic is simple. Humans want the smooth roads in the direction we want to go. And our emergent behavior is creation of the globally marked paths. Here we have this paved path and the trodden path. So now, since we are now, let's begin the last phase of our presentation, the pack collector experiment. In 90s, the researchers Beckers, Holland, and J.L. Denenberg experimented with the Stigmergy in robots, trying to create the mechanized pack collector based upon the cooperation of the maximally simple agents using the rules of the Stigmergy. Here we have our robot. The pack collector is essentially the definition of the simple robot that still uses the principles of the embodied AI. This was created in the early 90s, and even by today's standards, it would be pretty basic construction. Each of the collectors had 2 infrared sensors to avoid obstacles, and 1 plow with this pressure-sensitive switch, allowing it to sense when it's bumped into the packs collected. At the given programming, it would drop the packs when it's sensed running into at least 3 of them. By sensed, I mean that the switch mounted right there would trigger once the robot tried to shove 3 or more packs. The basic setup of the experiment was very simple. Here we have the area 2.5 meters by 2.5 meters with evenly spaced grid of the 81 packs. There were multiple experiments with the different number of robots. Here we have the 2 robots starting in the middle of the unclustered area. The purpose of the experiment was creating robots that can collect all of the packs roughly into 1 cluster. Now, which means that the experiment stopped only when all of the packs were in the same cluster. Now, we have the first phase. The robots are led into a ring, and they are starting to collect packs. As I have mentioned earlier, the robots were very basic, even by standard of the 90s. They essentially have only 3 behaviors. Drive in the straight line, turn around in the random direction after finding the obstacle, and go back a little and again drive in the random direction after trying to shove 3 or more packs at the same time. The second phase. Now, this seems like too little behavioral flexibility to actually correct packs. But thanks to the shifting probabilities of encountering given number of packs, based on the geometry of the cluster, it creates the dynamic where this bigger degree of the clusterization there is, the lesser the probability of robot just shoving the packs randomly. So the second phase of experiment is very quickly emerging patterns of the robots creating multiple small clusters. Now, it's pretty, as we can see, geometrically, it's pretty easy for given flow to just take apart one cluster, especially the smaller ones. This leads to the third phase, where where there are few large clusters. The only way the robot could dismantle existing cluster is hitting it at the angle. Now, this means that after some time, there is still probability of packs being removed. And thanks to how probabilities work in this dynamic, this means that the probability of smaller clusters being dismantled is bigger than the probability of the bigger clusters to be dismantled. And the bigger the cluster, the bigger the probability that these new elements will be added to it. This self-reinforcing feedback loop, means that given enough time, the robots will complete the cluster. Now let's look at the math behind the experiment. Starting with the for a size of the biggest cluster on the field in time. The different lines correspond to the different number of robots. As we can see, it took more than 6 hours for the single robot to complete the cluster. Now, the two robots could cut the time to roughly 5 hours. We can see that the biggest efficiency was reached by the 3-robot team, which managed to finish the task in roughly 2 hours. But for the 4 and 5 robots team, we saw the decrease of the efficiency. This happens because of the increasing number of the interactions between robots trying to avoid collisions. Essentially, this difficulty of the problem is too small for this number of robots to be beneficial. Here we have different look at the numbers. The number of clusters over time. As we can see, in all situations, this absolute number of clusters of packs quickly decreases. And the most difficult step is going from the small number of the big clusters to one big one. That's also the place where the singular robot got the most difficulty. Now, the mean time of the clustering run over multiple tests with the same number of robots shows clearly that the most efficient number for this experiment was the 3 robots. So, here we can see why these 4 and 5 robot teams were less efficient despite still utilizing the benefits of Stigmergy. Simply speaking, they spent a lot of time avoiding each other's instead of collecting packs. Putting it simply, they were overcrowded. Now we have the efficiency of the clusterizations based on the minutes per robots till the end. We can see that the 3-robot team was the most efficient again. So in conclusion, the Stigmergy describes the process of the complex behaviors emerging from the interactions between the simple agents and their environment. The process can be used to perform the tasks of optimalizations. We can easily influence the Stigmergy by utilizing the extra markers, like the road sets. Swarm-based solutions can encounter the roadblock in form of the overcrowding, where the communication between agents takes more time than actually doing something. And the sematectonic solutions enable us to create the machines that optimize their own working environment. Here we have this bibliography, which, as we can see, includes a pretty wide array of documents, especially the brief history of Stigmergy, which is more focused on the biology side of the issue, and includes pretty good description of how the process works in insects. And thank you for your attention. Now I will answer your questions. Yes, questions. Okay, I'm not seeing any question. Yes, I'm not seeing any question right now. Do we have any interesting remarks? Maybe something needs clarification. So thank you for your attention. We have one person thanking me for the lecture. Well, thank you. So now to the next speaker. Thank you very much. Sir,
yes, thank you for this great presentation, Lukasz. Also from my side, I think that the main lesson here is that Stigmergy is not magic, so you can model it, and so if you can model it, you can exploit it in the control system.
Of course.
And thank you for recalling the example from book of actually again about 20 years ago. As I told before, I think that these modeling problems are actually what is slowing the adoption of a certain set of concepts in embedding AI.
Yes,
now,
I also think that the modeling is a big bottleneck, but I think that better focus on these bionic methods of imitating nature could really help us. And the Stigmergy isn't limited to the physical spaces. It works equally well on the graphs. So it could be used to speed up the modeling process itself.
No, I couldn't agree more. Now thank you
again.